Today, I'm going to talk about the two theoretical physicists who are in part responsible for developing or inventing, rather, the so-called standard model for subatomic particles. One is Steve Weinberger, another is to be discovered from this talk. These two theoretical physicists had different philosophical ideas about their research, especially in relation to the reductionism. Reductionism in physics has been very popular since ancient Greek. As you know, Democritus believes that if you reduce the size of any material, ultimately you will see something indivisible called atom in Greek. On the other hand, Plato and his followers believe that ultimately, by reducing the size of any material, you will find something non-physical, but some geometrical shapes. These shapes are called the Platonic solids. We can argue that Democritus' atomic hypothesis is a physical model, while the Platonic solids are merely mathematical models. However, both of them believe that as long as we could understand such ultimate elements, then we should be rebuilt everything in nature around us and even beyond. So that could be the earliest time you can find the idea of reductionism. Of course, after discovering the atoms and eventually the subatomic structures, reductionism became much more popular among some theoretical physicists who believe that if we continue this way, then we should solve every fundamental questions in physics. So that is how the standard model was eventually introduced. Among these theoretical physicists who believe the reductionism, Steve Weinberger is a typical example. On the other hand, however, there are increasing number of physicists, especially theoretical physicists, who actually became critical about this reductionism and who argue that the complexity increase as the size increases. So this is an issue to be discussed today. Let's go to the blackboard. Whenever we're discussing the standard model, people would immediately think of Higgs because the Higgs particle is so important to building this standard model. Today, I'm not going to discuss too much about the Higgs particle. Instead, I will focus on the W-Boson. You can find all the elements of the standard model in this table. These elements can be divided into two categories. One is fermion, which is used to build the substance or material. Another is called the boson, which are responsible or to mediate the interaction among the fermion particles. Among these boson particles, W-Boson has been on the spotlight recently due to a latest report by the Fermilab. The mass of W-Boson should be slightly heavier than the previously reported value. If this analysis method is reliable, then the actual mass of the W-Boson is noticeably different from the one we know before. Some of them believe that that could, somehow to shake the foundation of the standard model. Obviously, among the mass media, this sensational headline has created a shock among the public, as well as in those particle physics community. Have you ever thought what is the motive this being reported? It's very strange, isn't it? But in my opinion, this is very suspicious. In the first place, the data they used is over 10 years old. So why did they report this early experimental result right now? Do they have some new algorithm which can better interpret their experimental data? Here are some what I call unintelligible or even unintelligent explanation by Fermilab. So first, let's say the beam had damaged the detector enough so that there was no way to cut our uncertainty. So that is nonsense, because a detector in an instrument is used to measure signal. Okay, if the signal is too strong, then you have to find another way to reduce the signal before they reach a detector. Another explanation by the Fermilab is that a decade of recorded data hasn't been published simply because of the difficulty in making the measurement at the required level of precision. So this is nonsense. How can you improve the level of precision of measurement after you have done this experiment over 10 years ago? Mathematically, by some magical algorithm? Aha, the last explanation will explain their motivation. They say a high energy E plus E, presumably that is an electron and positron collider, could answer this pretty easily. In other words, they probably have an agenda to developing another expensive instrument so that they can repeat the measurement of the mass of W-Boson in their lab. However, there has been always political and environment challenges around this high-risky investment. For example, this is a piece of the budget cut news in 2007. It's inevitable that the Congress will, from time to time, to evaluate the performance of these high-risky, zero economic yielding research centers. So it could be argued that the Fermilab had developed some strategy to inform the public in advance in the case of the budget cut. That is their motive, I think. My suspicion is by no means groundedness. In the early 1990s, there is a huge project going on in Texas, USA. The name of this project is called Superconducting Super Collider, or SSC for short. But something very strange happened. In 1993, due to a special Congress hearing in Washington, D.C., in which both Weinberger and another theoretical physicist were invited. This is old photo took when that SSC project is kicked off, in which you can see President Ronald Reagan. This is Weinberger, not the former Secretary of Defense, Weinberger, but the physicist I mentioned at the beginning, Steven Weinberger. And there is another physicist, should I say experimentalist, called Samuel Tin, or Tintin for short. And I can discuss about him further. But today we are focused on Weinberger and another theoretical physicist. Before we go to detail, perhaps it's necessary to mention why Weinberger was invited for this particular Congress hearing. In 1967, Steven Weinberger published his paper called A Model of Lepton, in which he outlined the strategy, how to possibly unify the electromagnetic interaction and the weak interaction. The key idea, as I highlight here, is so-called spontaneous symmetry breaking. This note will describe a model in which the symmetry between the electromagnetic and weak interactions is spontaneously broken, but in which the Goldstone boson are avoided by introducing the photon and the intermediate boson fields as the gauge fields. So that is the outline of this paper, very important paper, and for which he got a Nobel Prize. However, it seems that Weinberger consciously or even deliberately didn't mention the origin of this idea, namely the spontaneous symmetry breaking. So the question is, who is the person who had this idea first? Well, the answer can be found from the latest paper published by the Fermilab, together with their collaborators. Involved hundreds of authors in this paper. Okay, I have no time to go through them one by one, but I will just mention the reference used. Okay, so this is last sentence of this paper outlining their result. Notice the first paper was written by P.W. Anderson. P.W. Anderson is a second theoretical physicist I'm going to talk about today. This paper was published in 1963, a few years before the publication of Weinberger's paper in 1967. So logically, Weinberger should mention Anderson's paper in 1963, but he didn't. So this is two relevant papers he published. One is in 1958, another is in 1963, as the second one was used as the first reference in this important publication on standard model. Why? What is the reason? Let's find the explanation by Higgs himself. So this is something very interesting. The Higgs hypothesis was born in the midst of all these particle physics struggles to give mass to vector boson, including W particle, in relativistic gauge theories, in energy to superconductivity. Superconductivity sounds familiar as well. Indeed, the connection to superconductivity is made explicit by Higgs himself in his original 1964 paper, where he states that these phenomena, the Higgs mechanism of spontaneous symmetry breaking, is just the relativistic analog of the plasmon phenomena to which Anderson has drawn attention, quoting Anderson's paper in 1963. So Higgs said so, so Higgs wrote so. That's one reason that Anderson's paper was used as the first reference in this paper. Still, it's very strange. Many people still don't know who Anderson is, although P.W. Anderson, together with his teacher, Van Vleck, shared the Nobel Prize in Physics in 70. Here is some drama, see. During that Congress hearing, the chairman, just listen, what the chairman said about P.W. Anderson. This talk is after the Weinberger delivered his speech. So the chairman said, "Thank you very much, Dr. Weinberger. Our next witness is Professor Philip Anderson from the Department of Physics. I think that is applied physics at Princeton University." So that is his remark. Then Anderson replied, "Thank you. For the record, I'm not an applied physicist. I like to call myself a fundamental physicist as well. I am just a fundamental in somewhat different way." The chairman continued, "Was that because of the W particle?" Obviously, he learned this from the Weinberger a lot. "No," said Dr. Anderson. "It was the Higgs boson that I helped invent." I mean, for such an idiot person, you cannot hide your real contribution in public. Do you agree? 2 months later, after this hearing, the SSC project was aborted or terminated forever. The costs are huge. The original estimate of this project is just $4.4 billion US dollars. But by 1992, that cost had risen to $8.25 billion. Okay, and the total cost is equivalent to $18 billion today. You can see that how much money, how much taxpayers' money has been saved by P.W. Anderson. So you know who is P.W. Anderson now, but what he had done prior to that publication in 1963, well, I know because I was in that research field for over 10 years. Unlike many theoretical physicists, they always stayed alone, just thinking in mathematical language. P.W. Anderson actually choosing to work close to the people who do experiment. And the field they choose in the early age of his career is magnetic resonance, both nuclear magnetic resonance and electron paramagnetic resonance. So that is the field I worked before. So I know his contribution in this field quite well. So this is an earlier paper published by P.W. Anderson and P.R. Weiss in 1953, entitled "Exchange Narrowing in the Paramagnetic Resonance." Exchange narrowing. Exchange is a key word in building the standard model because every fundamental interaction in standard model is described by such exchange force in which the particle, the boson, mediate the interaction. Namely, the boson is exchanged by a pair of fermion in order to generate that interaction. So exchange force is a quantum idea, which was first discovered when we studied the wave function of helium. Unlike a hydrogen atom, helium atom has 2 electrons. Therefore, you will see, apart from the repulsive interaction due to Coulomb's repulsive force, you have to take into account of this quantum effect into account, which is associated with flip-flop of the spin of 2 electrons. And that interaction is called exchange interaction. Okay. Of course, eventually this idea has been eventually introduced to the study of nuclear and eventually the elementary particle studies. In short, as early as 1953, Anderson could theoretically formulate exchange effect on the detected magnetic resonance spectra. In other words, if the exchange interaction is strong, and then the line were getting narrowly, it's very strange. If you just consider the dipole-dipole interaction alone, then it always, according to Van Vleck, according to his teacher Van Vleck, it always generates the line broadening spectra in detected spectra. However, if the exchange interaction became comparable or even stronger than the dipole-dipole interaction, the observed line widths were reduced. So that is the famous exchange line narrowing theory. Notice that this paper was published in 1953. What happened next? Next year, in 1954, Kuba and Tomita published a paper entitled A General Theory of Magnetic Resonance Absorption. Why did I mention this paper in particular? Because later on, the so-called linear response theory became so important in physics and beyond due to the contribution of the Kubo. But where did Kubo get his first idea? The answer is the publication by P.W. Anderson and P.R. Weiss in 1953. So you know more about P.W. Anderson now. Furthermore, because P.W. Anderson is always called himself as a house theoretician, his primary job is to help physicists to interpret their observed experimental result. Of course, no doubt, he knows pretty well which experiment is good or poor. From this spectra of EPR, or namely the electron parametric resonance spectra, you can see that we can find the position of peak and their line width very accurately. This is another example use electron parametric resonance method, where a spin label made by nitroxide was used and sent into the bilayer of the biological membranes to report the local structural and conformational and functional information. That is how we use this very powerful and versatile experiment method to study the complex system, okay, including the biological system. By way of contrast, this is the experimental result to discover that, you know, that Samuel Dean, the Tintin, he discovered this particle in 1970s, that that is how this peak looks like. It's okay, we still can see the peak. However, this is experimental result recently used to claim that the discovery of Higgs boson. Look, without mathematical manipulation, one can hardly see the peak. So you can argue that Anderson knows which experiment is good and which experiment is not. Because after all, the physics must be supported by experimental. So there's no doubt about that. Here is the main reason that why P.W. Anderson thought we should terminate the SSC project immediately. One, science can be fundamental without being irrelevant. Two, money is important, but manpower and education are more so. And money affects this. Three, the term spin-off should be erased from the language So why did Anderson was so keen about this spin-off? Because he heard from the congressman during his appearance that they believe that the MRI, the magnetic resonance imaging technology, was spun off from the research of the particle physics, which is a nonsense, right? The MRI was actually developed from the idea exactly from the study of the magnetic resonance, where P.W. Anderson had involved for many years. Even in his 90s, P.W. Anderson was still active in response to various outrageous claims from the community in physics. Here is his remark on the string theory. My belief is based on the fact that the string theory is the first science in hundreds of years to be pursued in the pre-Baconian fashion without any adequate experimental guidance. So you know some story about P.W. Anderson now. I hope you enjoy watching this video, and see you next time. Goodbye.